video of a two-part series, we're going to introduce you to flow measurement using a differential pressure transmitter. The second part of our two-part series will take you through the process of checking the output accuracy of a differential pressure flow transmitter and show you how to recalibrate it if necessary. Flow transmitter calibration is the focus of our discussion, but let's review some other important terms first. We're going to define the terms range and span and zero and span adjustments. After that, we are going to explain how a differential pressure transmitter is used to measure the volumetric flow rate, explain why a square root extractor is needed in differential pressure transmitter flow measurements. Okay, let's go. We say that an instrument is calibrated when its output corresponds to a specific input across a specific range of inputs. Said another way, instrument calibration is a process where the instrument is adjusted in order to achieve the desired output range for a specific input range. For example, a current output type flow transmitter is calibrated for a volumetric flow range of 30 gallons per minute to 100 gallons per minute. When the transmitter produces a current output of 4 milliamps at 30 gallons per minute and a current output of 20 milliamps at 100 gallons per minute, a flow rate of 65 gallons per minute would produce an output of 12 milliamps. The input span of an instrument is simply its lower range value, often referred to as LRV, subtracted from its upper range value, often referred to as URV. For example, the span of the input range of 30 gallons per minute to 100 gallons per minute is 70 gallons per minute. Zero and span are the names of the adjustments made in order to calibrate an instrument. There are many ways to adjust zero and span. For example, they could be physical adjustments, such as potentiometers, or software-based push-button adjustments. A common method of flow measurement is done by using a differential pressure transmitter. The differential pressure transmitter, often referred to as a delta P transmitter, is placed across an obstruction such as an orifice plate. The orifice plate will cause a varying differential pressure drop across it as the flow through the pipe changes. Unfortunately, the differential pressure across the orifice is not proportional to the flow rate, but is actually proportional to the square of the flow rate. That's why in applications like this, we need a square root extractor. Sometimes this square root function is built into the transmitter, and sometimes a square root extractor is a separate signal conditioning instrument connected to the output of the transmitter. Do you remember when we said that the differential pressure is proportional to the square of the flow rate? In fact, the volumetric flow rate is directly proportional to the square root of the differential pressure. You might have seen this equation before, where Q is flow rate, and delta P is the differential pressure across the orifice. Let's do some math and see what happens. According to the equation, a flow rate of 90% would produce a differential pressure of 81%. There is a way for the flow rate to be directly proportional to the differential pressure, and that's by removing the square root from the equation. A square root extractor will perform this function. If you're still a bit fuzzy, it will all become clearer as we progress to part 2 of this video series. Let's review what we've discussed. An instrument is calibrated when its output corresponds to a specific input across a specific range of inputs. The input span of an instrument is simply its lower range value subtracted from its upper range value. Zero and span are the names of the adjustments made in order to calibrate an instrument. A common method of flow measurement is done by using a differential pressure transmitter across an obstruction, such as an orifice plate. The differential pressure across an orifice is proportional to the square of the volumetric flow rate. Therefore, we need a square root extractor.